side of the programme. Today, it's my pleasure to welcome James Cooper from the University of Liverpool, who will be speaking about erosion hazards and the economic damage to critical infrastructure in the river catchments. So this project was commissioned as part of the first call of projects and concluded in March of this year. I think it's the first time for this series of webinars that James will actually be wearing two hats. Firstly, he'll be presenting the work that he's been undertaking, but then he'll also be presenting the response using slides that have been provided by a contact at National Grid, who unfortunately can't be with us today. Again, as usual, there should be plenty of time at the end for Q&A, so post your questions as we go through. So this is just a usual start at the slide at the start of the seminar by means of a reminder. We'll have the presentation followed by questions. Please pop your questions in the Q&A and remember to use the upvoting facility to like other people's questions as appropriate. Microphones will be muted unless you're invited to speak. The session is being recorded and will be on YouTube subsequently. If you've got any technical problems, highlight these in the chat and someone will take a look for you. And just a reminder about social media stuff, there's a Twitter handle and hashtag if you want to tweet about anything today. And as always, there's loads more information on the UK Climate Resilience website if you want to take a look at that. So before we begin, there's just a few update slides regarding news from the programme. First of all, just to draw your attention to a paper published just recently. This was led by Helen Hanlon and examined the metrics relating to high impact weather over the UK and how these will change with different levels of future global warming from 1.5 degrees to 4 degrees above pre-industrial. So take a look at that. Next up is a Working Group 1 contribution towards the 6th assessment report, which will be released on the 9th of August, I believe. There'll be subsequent meeting on the 15th of September. So if you're interested in this, then please sign up. The link's shared there at the bottom. The meeting will hear from leading scientists involved with the report, as well as people involved with decision making on climate change actions. So if that's of interest, please register. And finally, just a reminder that the UK CP18 local dataset will be relaunched tomorrow. So please take a look at those datasets and also all the supporting material. Again, the links at the bottom. So without further ado, I'll hand over to James. So James, can you share your slides, please? I'm going to stop sharing now.
Thank you, Mark. Okay, so yeah, again, thanks, Mark, for the introductions and also for providing me with an opportunity to present some of the outputs from our 12-month proof of concept project. And as Mark outlined, this was funded in the first call of the UK Climate Resilience Programme. So the project involved 4 other investigators from Liverpool. There was Andy Plater as co-I and 3 research assistants, Xiaorong Li, Chris Feeney and Sam Godfrey. And the partners were National Grid, Waterco, Arup and Coya Green. Our project started in February 2019 and we were focusing on developing a new modelling and software platform to forecast how inland erosion hazards to critical infrastructure will change in a warming climate. So we assessed both physical and economic impacts of erosion in order to understand how the vulnerability of different types of infrastructure will vary with climate change. In today's presentation, what I want to do is focus on 2 case studies that showcase the capabilities of this new modelling and software framework, namely one case study looking at the broad feasibility of the platform in forecasting changing erosion hazards for a range of different critical infrastructure. And this example showcases our new capability to provide probabilistic event-based forecasts for different epochs in the next 60 years. and and predicting how economic damage is likely to change for those different assets. And the second case study is a much more focused one on a particular type of critical infrastructure, namely electricity transmission towers, and the threat posed by enhanced erosion to those towers, informing which towers require protection. And that particular case study is going to showcase our ability to produce continuous forecasts of erosion hazards. So why did we focus on erosion hazards within river catchments? So arguably one of the biggest impacts of climate change on critical infrastructure will be an increase in the frequency and intensity of storms, leading to more damaging flood and erosion events. Now, major advances have been made in the prediction of flood risk, how flood risk will adjust to climate change, and also major advances in being able to assess the vulnerability and resilience of critical infrastructure to river and surface flooding. For example, a quick search that I did yesterday in the Web of Science reveals that in the past 10 years alone, over 19,000 journal articles have tackled this particular problem. However, no such major advances occurred for erosion hazards in river catchments. So although there's numerous models that are able to predict river and slope erosion, there's been no attempt previous to this project to quantify the uncertainty and the risk posed by erosion hazards, to assess the future impact on critical infrastructure, and to evaluate the vulnerability and resilience of critical infrastructure, crucially to differing storm regimes. So at present, or at least before we started the project, I'll argue, is there wasn't any predictive modelling framework available that could support sustainable, resilient decision making in a warming climate. So why are erosion hazards important? Why do we need to consider them? Well, I would argue that really erosion hazards are of strategic national importance because they are wide-ranging, they're costly, and of critical importance to the vulnerability of assets, some of which I've shown here on this slide. So namely, erosion causes considerable considerable damage to key infrastructure such as bridges, roads, buildings, electricity towers, and dams, and also contributes substantially to insurance claims. So erosion accounts for 25% of valid subsidence insurance claims in the UK. And also erosion can cause damage to flood defences, and that's currently estimated to cost around about £80 million a year in England and Wales. And you'll see at the bottom in the bottom centre that the spillway collapse at Oroville Dam in California in 2017 was caused by slope erosion that occurred on the spillway, and that caused damage of more than $200 million and the evacuation of over 200,000 people. And furthermore, erosion of farmland can cause considerable loss of soil and nutrients, reducing crop productivity, or indeed destroying crops directly. Furthermore, erosion causes sedimentation in rivers, urban drainage systems, and flood defences, incurring high maintenance costs and reducing the resilience of those drainage networks to future flooding. So, for example, in England and Wales, maintenance costs associated with this sedimentation in urban drainage systems is estimated to be costing around £50 to £60 million a year. And of course, in recent days, the flooding in Germany has caused extensive slope erosion, scour and deposition of sediment within towns and cities, acting as a timely reminder that storm-related erosion impacts are severe and far-reaching. So to establish resilient and sustainable I would argue that we need to account for the potential risks that erosion hazards are likely to have in the future. So what are the kind of key questions? Well, because this no computational framework exists, unlike exists for assessing flood risks, we don't really know what the future risks are of inland erosion, slope and river erosion, and we just really don't have any kind of grasp on how vulnerable and resilient these assets will be to increased frequency and severity of erosion hazards. So stakeholders are facing difficult questions about mitigation strategies, and namely where do they need to act to make an asset more resilient, and when is that action required? Is it required now, or can that investment in improving the resilience of those assets to erosion hazards, can that be postponed and put in place at a future time? So in terms of the project objectives, really the idea was that we wanted to answer those questions by developing a new modelling framework and a suite of software tools that could be utilised for the probabilistic assessment, communication and mitigation of erosion risk. So for a more holistic and integrated assessment of the scales and consequences of erosion, we assessed the vulnerability of assets by looking at the projected economic impacts. And these metrics were developed to assist stakeholders in priority setting and decision making, helping them answer those two critical questions. And the final product was a pilot decision support tool that visualizes and communicates this erosion risk. So here's a high-level overview of the platform, just so you get some sense of what the different components are, and I'll be discussing some of those in more detail as we go through. So the platform uses exposure data to feed a hazard model that predicts the extent and probability of erosion. And then from these hazard estimates, a damage model predicts the expected annual economic damage to each type of infrastructure. And then these data feed into a decision support tool that allows the hazard and risk to be visualized, providing risk heat maps that show where the risk lies. So i.e., you can see which assets are at risk, as well as showing why they're at risk. So for example, for a particular building, you'd be able to say it's at risk due to bank erosion, or a bridge is at risk due to bed scour. And this tool also then displays when this risk is likely and an estimate of economic damage. And I'll give you a brief demonstration of that decision support as we go through the presentation. So the first case study I want to present is one where we trialled our new modelling framework on Cockermouth, a town in Cumbria, northwest England, to highlight its ability to determine current and future erosion hazards to different types of critical infrastructure. Now, we chose this particular case study for three main reasons. One is that this area is historically prone to severe flooding and erosion damage from storm events, particularly so in the last 2 decades. So there's been severe damage in storms in 2005, 2009, and 2015. So, for example, in the storm in 2009 inundated large parts of Cockermouth, severely damaging 2 road bridges and demolishing a key footbridge. And thus these climate change projections that I'm going to be showing you are of strong interest to stakeholders. And finally, from a modelling point of view, this is a real challenge to try and model this kind of system, because it contains the confluence of 2 rivers. So you're having to simulate what's happening in 2 rivers, in 2 catchments. And also there's a mixture of different types of rural and urban fabric, as well as also a range of different asset types for us to target. So next, I just want to briefly outline how we go about modelling erosion hazards. So just giving you a little bit of an overview here is that the modelling involves 2 steps. First is at the catchment scale, we use projections of rainfall for differing annual exceedance probabilities, or return periods in old money. And we predict how much of that rainfall is going to generate runoff on the slopes, and then how much of that is going to actually flow into the river. And from that, we can then estimate what the river discharge will be. And we use the estimates of runoff on the hill slope in the catchment mode, i.e. that overland flow, that surface flow, to predict the amount of soil erosion that's going to be caused by sheet, rill, and gully erosion. And next we use the discharge estimates from that catchment mode, and they feed into a reach scale hydro erosion model that predicts the river depth and velocity, how much water goes over bank during a flood event, and then how that routes over the floodplain. And from those estimates of what the flow conditions are, we can then predict what the floodplain scour will be and the bed and bank erosion that's generated. So in terms of generating these projections of rainfall, we use the UK CP18 CPM 2.2 kilometre resolution projections to characterize the localized changes in rainfall over the next 60 years for epochs 2021 to 2040 and 2061 to 2080. So the graph here shows the estimated total rainfall for 3 annual exceedance probabilities, namely 3.3%, 1%, and 0.1%. So that's a 1 in 30 year, a 1 in 100 year, and a 1 in 1,000 year. So in other words, as we move from the left to the right, we're looking at storms that are becoming less probable and large magnitude. And we examine 3 different storm durations. The numbers in the figures next to the data points are ratios between the rainfall of each future epoch and the current climate conditions or the baseline. In other words, the proportion by which these rainfall totals increase through the different epochs. So compared with the baseline, the totals for the 2 epochs increase, reflecting, of course, a warming climate. For epoch 2021 to 2040, rainfall totals increase as storm duration lengthens, as you might expect. For epoch 2061 to 2080, however, the rainfall totals show that the climate is moving towards shorter duration events with higher rainfall and longer duration events with less rainfall. So in particular, rainfall totals for 6-hour storms are smaller than those for 3-hour storms. And you'll note that that doesn't occur for current conditions, nor for 2021 to 2040. So what does changes mean in rainfall actually mean in terms of future erosion hazards and economic damage? So this is a screenshot of our web-based mapping platform for stakeholders, what we call our decision support tool, which I will just demonstrate in a moment. So this mapping software is designed for the non-specialist, so it acts as a visualization and interrogation front end for the model simulation data that sits behind the interface, so it doesn't require any user modeling. So the tool enables the user to explore the areas and infrastructure that are presently at risk in terms of likelihood and extent, as well as also their vulnerability in terms of economic loss, along with the extent to which this risk is likely to change with climate. So I'm just going to give you a quick demo and share a different screen, and so that you can get some sense of what this software looks like. Okay, so hopefully you should be able to see a map with some visualized results. And so this is our decision support tool, where what we've got is slider bars at the top left, where we can change the magnitude or the probability of the event. So in this case, we've got in old money 1 in 30 year, 1 in 100, and 1 in 1,000 year return periods. We can also change the rainfall duration, and we can also change the climatic conditions, whether that be the baseline current conditions or through to those 2 future epochs. We're also able to overlay, as well as displaying, for example, here the extent of flooding, we're also able to overlay the hazard that occurs due to that flooding. But crucially, we're also able to overlay the amount of erosion and deposition that's occurred, with the yellow colours signifying where there's been significant erosion, and the red where there's been significant deposition of sediment. But also what we can do here in the box on the left-hand side is, for the different types of infrastructure, is project what the economic cost will be for those different types. And so you can see the differential vulnerability of those particular assets. So just this example is showing is for a 6-hour storm event, a 1 in 30 or 3.3% annual exceedance probability storm event for current conditions. And what we can do is we can just look at what it will be in the next 20 years. And you can see here quite markedly is a large increase in the extent and magnitude of erosion and deposition that occurs due to this higher magnitude or projected higher rainfall totals for this particular storm. Now, what's really key about this is it's updating the costs every time you use the slider bars, but crucial, and as I'll hopefully be able to show a little later, is this modelling provides really high resolution information on the impacts on individual assets, whether it be bridges such as of which there's many, as some of you may well know, whether it be bridges along the River Cocker in this case, and also along the River Derwent, as well as also enabling you to understand which roads are at risk and which buildings are at risk as well. And this is because erosion is highly patchy, so being able to do this fine scale resolution modelling is really quite important to understand which of those assets are likely to be at risk. So I'll just stop sharing there and go back to the slides. So what I just want to do here is just summarise some of the things that I just showed you in that short demo. So here's an example of erosion maps for a 6-hour storm and for the 3 annual exceedance probabilities. So again, here the positive numbers are denoting the deposition of sediment, and negative numbers are signifying where there's scour or erosion. So the areas that are susceptible to erosion or deposition increase from that baseline to 2021-2040 quite considerably. You'll see that there's a transition from the erosion and deposition mostly being confined to the river channel, the banks, and small areas of the floodplain, through to causing slope erosion on agricultural land and recreation grounds, including at Cockermouth Cricket Ground. Bad news for cricket fans. However, when we look at epoch 2061 to 2080, as a result of those lower projected rainfall totals for 6-hour storms that I showed earlier, the extent of this erosion and deposition reduces in comparison to 2021-2040. So in terms of the significance of these changes to critical infrastructure and key buildings, there's really quite remarkable erosion and deposition, depths of up to 4 to 5 meters, which is really quite considerable in and along the 2 rivers, particularly along the River Cocker, making buildings along the river bank in particular susceptible. So, for example, the castle, which has nearly got destroyed in the Storm Desmond floods, is a significant threat to projected changes. And also the United Utilities wastewater treatment works, which is based along the River Derwent in the western part of the city, is also likely to be at risk. Because of the density of bridges within this particular town, it also means that 5 bridges that are connecting the east and western parts of the town are also under high risk of being damaged and also potentially collapsing with future changes in storms. And we'll also find that that some of the roads are also forecasted to experience erosion, causing instability in the road embankments. And there are also large areas of sediment deposition, which actually we saw in some of those pictures from the recent flooding in Germany. And of course, that requires removal, which is a cost, but also potentially blocks access to emergency responders during storm events. Also, you'll see that as we go through into the future, that that agricultural land is experiencing quite significant erosion and deposition, depths of up to 2 meters. So it's signifying there's rill and gully formation, and this is likely to have major impacts on soil productivity and crop yields. So to estimate the economic damage of these hazards, and I'm sorry to include an equation, this is the only equation you'll be relieved to hear, is that to estimate these economic damages, we calculated the expected annual damage, or EAD, for each infrastructure type and also for each epoch. And so the EAD is the sum of the annual economic damage for each of the annual exceedance probabilities. In other words, the EAD equals the monetary impact of each storm multiplied by its probability of occurrence. So, or put another way, the EAD is the expense that would occur in any given year if monetary damages were, from all hazard probabilities and magnitudes, were spread equally over time. So the reason why we look at these EAD estimates is because the difference in the estimates between current and future climate conditions represents the cost that could be averted if appropriate interventions are put in place. Thus, these estimates show which assets are vulnerable and which require investment now, and those that are likely to be vulnerable and require investment in the future. So I'll show you what I mean in the next slide. So what this shows, this graph on the right hand side shows how these expected annual damages are going to change from the current conditions all the way to the epoch of 2061 to 2080. And you'll see that those costs are broken down according to those major types of infrastructure that we've been looking at: buildings, roads, bridges, agricultural land, and the urban fabric in terms of deposition of sediment within that urban fabric. So what you can see from the graphs is it's pretty clear that bridges have the largest expected annual damage, and then that's followed by then the urban fabric. And just with those bridges, just to note that expected annual damage is pretty high. We're talking around about 4 million to 6 million, because when these bridges collapse, it costs an awful lot of money to reinstate or to rebuild those new bridges, as we've seen in previous storms in Cockermouth and in Cumbria more widely. The second highest costs come from the urban fabric, estimated between 1 to 4 million, and then agricultural land, buildings and roads. And from the current climatic conditions, the epoch 2021 to 2040, these costs increase for all of the asset types. However, when we look at epoch 2061 to 2080, you'll see that actually those costs reduce, and that's reflecting the fact that the 6-hour durations in this particular epoch are projected to produce much less rainfall and therefore cause less erosion and deposition. And the other thing to note here is that although buildings and roads have the lowest expected annual damage under the current climate conditions, these types of infrastructure are likely to experience the largest percentage increase in costs over the 60-year period. So these estimates, along with the erosion maps, clearly show that bridges require investment now to avoid costly failure. And intervention may also likely be needed within the next 20 years to avert the economic costs associated with significant sediment deposition in the urban fabric and erosion damage to roads and agricultural land. Okay, so now on to the second case study, and the purpose of which is to demonstrate how the framework can be used to examine the impacts on a different type of infrastructure, namely electricity transmission towers, using a different approach to provide continuous time series of erosion hazard estimates. So we've been working with National Grid to apply our platform to assess the risk posed to towers in the upper reach, in an upper reach of the River Mersey, just southwest of Manchester. So along this stretch of the Mersey, there are 40 National Grid towers, which you see in those purple blobs, which are in proximity to a channel that is prone to flooding and river channel change. So 10 of these towers are located within 50 meters, just 50 meters of actively eroding riverbanks. And so this reach is of particular interest to National Grid because it is laterally dynamic. And what I mean by that is that if we look at reconstructions from historical Ordnance Survey maps, it reveals that the channel has changed its form and migrated its position over time, and has sometimes impacted on the towers. So for some of the towers, there is some existing protection in place, and they are putting, and National Grid have additional monitoring is required to assess the changing vulnerability. But of course, the climate change projections are of particular interest because they need to know in the future which of those towers might need further protection or change in protection, which might need some further monitoring, or in the worst case scenario, which of those towers might need to be relocated to a safer spot. So since river channel change is the significant issue at this particular part of the River Mersey, a continuous simulation of erosion hazards for the next 30 years was required. So this is required because it then allows the model to route and deposit eroded material within the fluvial system and update the channel position daily. So for that 30-year period, we simulate the flow time series, the erosion, and the river channel position every single day. However, as I'm sure most of you know, the UK CP18 CPM 2.2 kilometre projections do not provide this continuous rainfall. So thus, based on previous estimates of changes in peak flows from the RCM projections, which were at a coarser resolution of 12 kilometers, we explored 5 discharge scenarios where the peak flows, based on the observed time series, as you'll see there on the graph, were increased by 10%, 20%, 30%, 40%, and 50%. So this amplification has the effect of increasing the annual frequency of what we've termed geomorphically effective flow events, i.e. these are the flow events that cause channel change, which we identified as ranging between 75 and 105 QMEX for this particular reach. So what effect do these changes in the hydroclimate actually have? Well, here's a map of how erosion and channel position is likely to change for those 5 different scenarios, with again those positive values denoting deposition and negative values erosion. And you'll see that the extent and magnitude of erosion, as you might expect, is projected to increase over that 30-year period. And of course, that enhancement in erosion and deposition is greater for those higher flow scenarios, particularly 40 and 50% increase in the magnitude of the peak flows. Of particular note, which I'll explain why this becomes relevant as we go through the rest of the presentation, is that this channel change causes 2 large meander cutoffs. So the meanders totally get cut off, and we get almost a much straighter channel being incised and diverting the flow away from those meander channels. And that has the potential then to divert that flow and that erosion towards towers that otherwise would not be susceptible. So here is an example of a erosion risk map, showing the locations of each of those towers in those purple blobs. And we're displaying this in terms of the depth of erosion and deposition. And what we also can do is then project onto these black arrows, which show the direction of the channel change during that period. So we get a sense of how that risk is likely to change through this channel migration. And so it therefore provides information on not only being able to see visually which of the towers are in close proximity or directly at risk through erosion, but also shows you why, i.e. what the processes are that are causing that, whether it be this channel cutoff, whether it be bend expansion, or whether it be bank erosion. And of course, by knowing the type of hazard that exists, enables you to then use the best type of erosion control intervention. So what we can do is we can then turn these maps into a time series of actually what's going to happen in terms of erosion and deposition at each of these towers, in order to work out which of these towers are at risk. Now, there's a lot of information on this particular plot, but what it's showing you here is in the different colors is the severity of the erosion and deposition, the location of these particular towers. Now, National Grid use these funny coding systems for each of these towers. But what's of particular note here is that what we're looking at is how the severity of that erosion changes from 2020 to 2050. So those green colors are where we have slight erosion or deposition, and the red areas are really severe erosion. And what it shows is that luckily the majority of these towers are actually not going to be at risk for the next 30 years. But however, 4 of these towers are not going to be so lucky, and you can see those, hopefully see that through these time series. So these 2 towers. So 2 of the towers experience slight erosions, and these are the negative numbers in terms of on the y-axis. They experience slight erosion at their location, and then they progress to suffering severe erosion. One at the year 2030 and another around 2035. 2 other towers experience significant amounts of overbank sediment deposition, and while not as serious an issue as erosion for tower stability, this deposition can affect servicing and monitoring of these towers by blocking access to these towers, and can, in some cases, if it's considerable, put undue pressure at the base of that tower. So just in case you're ever walking along this stretch of the River Mersey and you fancy searching out these towers, well, here they are. These are the ones, these are the 4 out of the 40 that are at risk due to enhanced erosion. So the Carrington and Urmston towers, they're likely to be impacted by those meander cutoffs I mentioned earlier, because it's rerouting the flow in their direction. And the Flixton tower by the bend is likely to be impacted because that bend is going to expand and migrate towards that tower through enhanced bank erosion. So what this map shows, along with the other maps I showed for Cockermouth, is really the highly localized impact of erosion. So not only in its magnitude, but also in the nature of the problem it causes, and therefore really showing the need to produce asset scale simulations of these hazards. So what do we do with this information? Well, here is the table we presented to National Grid once we've done all of these simulations, which and the details of which are not particularly important. It's just the concept here that I'm showing this table to reveal that you can use these simulations in order to outline which of those towers are at risk, when they require intervention. But as you can see on the far right column, also what intervention, what erosion control is actually required. And that, of course, is based on knowing what the particular hazard is, or the cause of the hazard is at that particular tower location. So here, what I want to do now is discuss what the relevance and importance of this work is to National Grid. So unfortunately, my contact in National Grid is not available for this webinar today. However, he has kindly, we have had discussions, and has kindly allowed me to compile this response into the following slides. So firstly, some background about National Grid and the importance of understanding environmental risk. So electricity assets such as so in terms of the actual network and what is actually needed to be protected, so the National Grid network has 21,990 steel lattice towers. Those towers were steel lattice towers that we were looking at in the River Mersey, and that supports 14,000 kilometres of overhead power lines in England and Wales. And the National Grid, due to environmental risks, are inspecting the condition of around 3,650 towers a year. Now, electricity assets such as towers and substations are integral in supplying consumers with power. So these assets have been designed to withstand a variety of environmental conditions, not only through flood risk and wind risk, but also things like vegetation growth and so on. However, the increasing number of extreme weather events could expose these assets to a greater risk than they've previously allowed for. So to ensure this network continues to provide an uninterrupted electricity supply to its millions of customers, the ever-growing complexity of environmental risk needs to be constantly monitored. At present, all risk notifications, i.e. whether a tower or a substation indeed are at risk of environmental impact, are manually reviewed by the control room, and they're supported from other departments within National Grid, including the environmental engineering team. And so when these risk notifications come through, it requires experienced human interpretation, which is just based on knowledge of the geographical area, to get some sense of how severe or likely that impact is going to be on electricity supply. So to give you some sense of how many of these alerts come through, that during stormy weather, as many as 10 alerts can come through in a day. So once these alerts are reviewed, the severity of the notification is graded and categorized according to a RAG system, red, amber, green system, and they're characterized to allow for appropriate action. So that could be a mitigation response, for example, to be initiated before there's any kind of environmental threat that impacts the network, and in other words, impacts the ability of National Grid to supply electricity. So the unfortunate thing with this is, because it's a manual process, is it's time consuming and of course resource intensive, and is reliant on the skills of, in particular, the environmental engineering team to interpret what that risk is based on their own understanding of the particular sites. Now, when lots of alerts are coming through, this can put pressure on the control room, And of course, what that can do is limit their ability to recognise any kind of escalating environmental risks. So in the event of an emergency, often internal experienced stakeholders from within National Grid are called upon from the different business areas to evaluate the incident frameworks and allocate the resources, such as defence measures or mobilising operatives. And failure to do so can result in additional pressure on the network and its ability to maintain electricity supply. Now, at present, the environmental engineering team can only make a qualitative assessment of what that future risk will be based on the history, the historical changes at those sites, and their sort of strong geographical understanding of the locations. But they cannot explicitly account for the future changes in hydrological regime. So the new modelling platform that I presented here provides the National Grid with this quantitative analysis of future risks. So it's allowing, therefore, the environmental engineering team using quantitative data to assess where that risk lies, why there's a risk, and then helping them then to determine the best response to that risk. So both in an operational and strategic sense, it allows that environmental engineering team to decide whether there needs to be further monitoring to assess the vulnerability of the tower, if erosion control is required at that site to protect the asset, or perhaps in some cases whether that control is required further upstream in order to lessen those impacts further downstream on their assets, or it could be in that worst case scenario of actually having to relocate that tower. So ultimately, this allows National Grid to optimise their response to environmental risk, allowing them to focus their resources on those towers that actually are at future risk and need some mitigation response. So ultimately, this will lead to cost savings for National Grid and less disruption to their electricity supply. So I just want to end really by saying thanks very much, everyone, for attending and listening to my presentation. And I'll hand over to Mark. Thank you.
Super, thank you, James. That was a really interesting presentation, and it looked like a pretty smart and useful decision support tool that you've developed there. So there are a few questions in the Q&A, and one of them is around where did you source your vulnerability information from, and can you say a little bit more about the damage model? I think that was in one of your earlier slides, because obviously you've got lots of information on the hazard, but to create a risk-based product we need to bring in vulnerability to the exposures. So are you able to say a little bit more about that?
Yeah, sure. Thanks, Mark. So as I said, we were looking at vulnerability in terms of those kind of direct economic impacts. Now, as some of you may well be aware, there's many damage models for flooding where you look at the depth of flooding for the different asset types, and the depth of flooding influences the amount of economic damage that's caused. So we used actually the same approach, but based on the amount of erosion, the depth of erosion, or the depth of deposition. So in other words, you produce these non-linear curves which show how that the cost escalates as the depth of erosion or depth of deposition increases. So to give you an example, for let's say for bridges, is you would at lower depths of erosion and deposition, it may be that all that's required is an inspection team to go out and to inspect that there's not likely to be any further damage to that particular bridge. Whereas, of course, if you get to a critical depth of erosion where one of those piers could well be scoured and damaged, and then you've got a cost associated with refurbishment. And then in the really extreme cases, if you have collapse, then you're talking about a cost related to then rebuilding that whole bridge. And so we repeated that process for the different types of assets. And so we got that data from various different sources. And I must acknowledge here, it is difficult to get hold of this information. So, whether it be from insurance companies, what the typical costs are, whether it be from stakeholders, how much does it cost them to send out a response team? And that comes in various forms. Sometimes you'll get, for example, the cost that it will be to remove sediment from a road in terms of the cost per square meter. Others you'll get the cost per bridge. So it is quite complicated to bring all of that kind of quite varied information into a damage model. So, I think given those uncertainties, we were keen just to focus on what those direct economic damages are. But I think have to recognise, of course, there are many indirect costs as well. So particularly for bridges, I mean, you think looking back at the Cumbria floods of, over the last 2 decades, when one of these bridges goes out, it's not just the cost of then refurbishing it, replacing it, it's also the disruption in terms of the movement of people, particularly from one side of the town to the other. So for example, when the Calvert Bridge went out in Workington, it was estimated it was costing £500,000 a day in terms of loss of revenue, because people weren't able to efficiently move across from one side of the town to the other.
Super, thank you, James. Question from Chris Bromley at SEPA. He's just wanting to check in terms of what erosion includes. Does this extend as far as landslides?
No, it doesn't. So what we're talking about here is, so in terms of the river, we're talking about being able to understand what the bed scour is, what the bank erosion is, and then any scour that occurs on the floodplain due to floodwaters. And then when we're talking about the hill slopes, we're talking about slope erosion. So we're talking about sheet erosion, which is the kind of early stages of a rainfall event, through to rill erosion and then gully erosion. It's an interesting question about landslides because, of course, with the Germany floods, we saw those landslides being caused by the instability at the toe of the slope due to the erosion that was occurring because of the floodwaters. Now, so there is a possibility in the modelling framework to include that, to include landslides in the sense of how the instability of that slope changes because of surface erosion. So you could look at how that susceptibility changes as a flood event occurs or as rill or gully formation occurs on the slope itself. And then looking at the slope angle, working out what therefore the susceptibility would be of a landslide occurring. So I mean, I would be very keen to explore that in the future. So I think that's a very good suggestion.
Super, thank you. That was his follow-up question actually, is how could this be extended? There's another question on a similar lines actually. So could this be used or adapted or extended to assess vulnerability of sewer or water pipes to erosion? Yes.
So so we had actually, it links back a bit to what I was saying about National Grid. So we were looking at the towers, these kind of surface assets, but they also have buried gas pipes. Just in this way, of course, sewer pipes are buried as well. And they gave us some examples of where these gas pipes have been exposed due to flood scour. So, I mean, there's absolutely no reason why you couldn't do this. No, if you've got that asset information, the locations of those sewer pipes, the depth of those sewer pipes, you could quite easily then work out this by simulating the depth of erosion that's occurring, the likelihood, therefore, of that sewer pipe being impacted by a storm event. I think in terms of urban drainage systems, this is something that I think is another extension for the model, is that I'd be very interested then to see with those surface drainage systems how sedimentation caused by the erosion of sediment being deposited within the urban fabric, how that then reduces the performance of those surface urban drainage systems. Suds, for example, get clogged up with sediment. You've got your drains getting clogged up with sediment. And it'd be interesting then, therefore, to see how that changes the vulnerability of a particular location to future flood events if you've got all these blocked urban drainage systems.
Super. There are quite a few questions actually, or more on the user side, so I'll probably try to wrap those all up in one question with many different parts to it. So you mentioned that soil erosion it was the cause of something like a quarter of subsidence insurance claims. So have you shared this information or this tool with the insurance industry? Another question is, have you shared this with local authorities? And then the final question on a similar vein is, have you shared this with the people of Cockermouth or where the other case studies was, and what was their reaction and how do we engage people? So 3 questions there, all about application and users.
Yeah, so I think in terms of local authorities, we're actually mainly due to a connection with an ex-PhD student, is starting to look at this in terms of the Sefton Council, because that's local to us in Merseyside, and looking at applying this framework to understand what the risks are that are posed to some of their assets. I mean, particularly local authorities are interested in the damage to the roads where they manage those particular minor roads. In terms of sharing the results with the public, not as yet. However, we are very much hoping to run an event with the Cumbria Flood Resilience Forum, which has representation not only from the public but also the local authorities and also many of the key stakeholders. I suppose we're at that sort of critical stage now where we've got the results, and we've now, as you hopefully have seen, can start to put some numbers behind those projections. And so this is the stage where we want to now really go out and start to disseminate those results to numerous other stakeholders.
Excellent. And then final question is, you've kind of alluded to the final part of your answer there, but where do you see the next steps for this piece of work? As you said, it was a 12-month piece of work that has now culminated. So where do you hope to go with it now?
Yes, certainly we're going to continue with our work with National Grid. So we pleased to say we've got some further funding to continue that work with National Grid. We also, for the UK Climate Resilience Programme, there's the Embedded Researcher Programme, which is the call is just out now at the moment, and we're putting together a joint application with EDF, and that will be looking at using this framework to estimate the vulnerability of their nuclear power assets, not only in terms of power generation now, but also doing some long-term continuous forecasts of erosion hazards to see how the decommissioning phases of their plants will change through time. We're particularly focusing on the energy sector at the moment because we've had very strong interest from them. But I think there's certainly, I think the transport sector is certainly something that we would like to get much more involved with. I think although Cockermouth is unusual in the sense that it's got a lot of bridges, a high density of bridges, clearly bridges and roads are important assets that are likely to be impacted by erosion. And I think we need to do much more work there to engage with stakeholders to take that element of the work forward. I think the other thing that could be interesting to look at, which I think is a real research challenge, is that we're doing these long-term projections, but what about when a storm event is forecasted to occur? So Mark, from the Met Office, you can receive all the information several days before and when a storm event is likely to hit. But can you use that information to provide real-time projections of what impacts of those storms are likely to be on infrastructure? So not only in terms of flooding, but clearly also in terms of erosion. So going to a real-time forecasting, certainly the information we've got from those stakeholders that own and manage these assets is that's the sort of focus they would like for us to consider in the future.
Super, thank you, James. That's all the questions in the Q&A. Thank you for both of your presentations, actually, both from your perspective and also the user perspective. That was great. I'm sure if there are any further questions, people can get in touch with you directly, or if there's anybody interested in collaborating. It's great to hear that you have a few further avenues to explore, both through UK Climate Resilience and elsewhere. So I'm just going to share my screen. Just hopefully you'll be able to see this. This is final slide before we conclude for today. This is largely to highlight upcoming webinars. We're taking a little bit of a break over the summer and then reconvening at the end of September with Rachel Perks from the Met Office, talking about the work that she's been doing in conjunction with others to develop a coastal tool. And then mid-October, there's another webinar for you to put in your calendars where Andrew and Chris from DEFRA are talking about UK government approaches for domestic adaptation and resilience. So just remains for me to say thank you very much for those of you who are able to attend, and this video will be made available on YouTube shortly. Thank you for your time. enjoy the rest of your day. Goodbye.